Okay, so on Monday we were basically considering rotations. We continued considering rotations, and we first looked at what happens when we rotate our coordinate axis. It's just our three-dimensional Euclidean space. And we had seen that the rotation operators we can write in terms of what we call the generators of rotation, these 3x3 matrices, which has entries. These are defined to be Hermitian, and it basically has only, if you consider rotations in the xy plane, it's just a matrix with only two non-zero entries. All the other entries are zero. And these are the operator that creates rotations around the z-axis is given by this exponential. Well, there is just a bit of convention difference between the book and what we had done up to this point. Basically, the book considers what we call active rotation. It's the vectors that are rotating. But if you rotate a vector, let's say, by an angle theta around some axis, in terms of its components, what happens to its components is exactly the same thing as what would happen if you rotate the coordinate axis in the opposite direction. So at least in these first few pages, there's a sign difference between what is written in the book and what we have derived. And basically, at the end of the day, we had derived this commutation relations of the four generators of rotations between the two coordinates. So this is, of course, just what happens to the just ordinary vectors. Now, the problem is when we go to the Hilbert space, in quantum mechanics, we are dealing with vectors in Hilbert space, or the directions in Hilbert space, to be more precise. So if you, and these directions, if you rotate your states in real space, your system in real space, it should somehow modify your kets. So let's say if you have a particle that is localized somewhere at this point, if you rotate this by an angle theta, you should obtain a different ket, which should describe a particle that is localized somewhere over here. So, and this operation, the operator that changes your initial ket, which has your particles localized somewhere over here, to the final ket, which has your particles somewhere over there, it should be a unitary operator. First of all, it should be unitary, it should be linear. It should be unitary because it should conserve probability. And all the operators in quantum mechanics, we assume that they are linear. And furthermore, for every rotation in three-dimensional space, there should be some corresponding unitary operator in our Hilbert space. So we basically define what I denoted by this D over here. What this D represents is, you can consider that D basically as a function. You give it a 3x3 matrix, which represents rotations in our three-dimensional space, and it gives you an operator in the Hilbert space. So it's a function from our 3x3 matrices to operators in the Hilbert space. And this function should have certain properties. For example, if we have two rotations in real space, it basically corresponds to a single rotation in three-dimensional space. It should be the same for this D operator. So if you have two operators, that corresponds to these two rotations. If you multiply them, it should be the same as the operator corresponding to a single rotation. And since every rotation has its inverse, its representation should also be an operator, a matrix. There's a corresponding operator. If you consider the inverse operator, there will be the corresponding inverse matrix. There will be the corresponding operator, and these two corresponding operators should be the inverses of each other. And no rotation should basically correspond to the identity operator. No rotation means we have the identity matrix. And if you don't do any rotation, nothing should change in your Hilbert space. So this is our identity operator. And we assume the associativity basically because the rotation matrices in three dimensions have that associative property. So basically what we are saying is whatever mathematical structure we have in our three-dimensional space for rotations, we should basically copy that structure to our Hilbert space. And the way we copy it through this function B. And then we said that, okay, since in our three-dimensional Hilbert space we have these generators, MZs, well, in the Hilbert space we can also define some generators of these rotations, which we call J, Jx, Jy, Jz. And since we are basically copying all the mathematical structure from 3x3 matrices to our Hilbert space, it also holds the similarity continues even for the properties of the generators. So Mx and My, they are 3x3 matrices. If you take their commutator, it should be, with the notation in the book, it should give you I times the generator of rotation in the Z direction, which is a 3x3 matrix. If you carry it to our Hilbert space, the generator for rotations around the x-axis in the Hilbert space, Jx, which is an operator, not a matrix, is commutator with Jy, which is another operator. It should be I times Jz. Now, these Jx, Jy, Jz, they are operators. They are not 3x3 matrices. Of course, every operator in Hilbert space, we can show it as a matrix, but that dimensionality of the matrix will depend on the dimension of the Hilbert space. It doesn't have to be 3x3. And in fact, we had one explicit example. We had these spin matrices. Now, we know that we already had seen that we can represent them as 2x2 matrices. First, we had shown that they do satisfy the commutation relations. You see, the thing is about these Jx, Jy, Jz operators, we don't really know much about them, except then that they satisfy this commutation relation. Well, that basically tells me that as long as we have three operators that satisfy these commutation relations, we can treat them as rotation matrices, rotation operators. And in fact, here we had made an explicit example that, for example, if we have as the Sx, when we look at the expectation value of Sx, and then we rotate our kets, after some lengthy algebra, we had seen that this is how Sx transforms. And similarly, you can drive how Sy transforms. If you would drive it, you would just get this is Sx times sine theta plus Sy times cosine theta. But this is nothing but what happens to a vector in three-dimensional space when you just rotate. What happens to the x and y components of a vector if you rotate your vector around the z-axis by an angle theta. So at least we know that everything seems to give us a consistent picture. And these Sx, Sy, Sz's, they are actually our vectors, spin vectors. And under rotations, this just shows us that if we take Sx, Sy, Sz as also the generator of our rotations, they just rotate as a matrix. Now, this was a particular example of spin 1/2, but you see, if you can basically do the same thing with an arbitrary system. We just looked at, for example, the Jx. We don't know. The only thing we know about the Jx operators are how they commute with each other. That's the only thing we know at the moment, at least. And at the end of the day, when you take the expectation value of Jx without knowing the spin of the system, or what the explicit form of these matrices are, if you rotate your system using Jx, Jy, Jz as our generators of rotation, indeed Jx transforms as just the x component of a vector would. So at least now we know two things, that our description of rotations gives us a consistent framework. Secondly, Jx, Jy, Jz, they are actually vectors. Their expectation values are vectors in real space. Again, I repeat, we don't know what Jx is. Its explicit form, at least. We can write it as a matrix, etc. But we definitely know that its expectation value behaves like just an ordinary vector. Now, any questions up to here? Well, this is what we had derived for the rotation matrix or rotation operator for rotations around the z-axis for the spin 1/2 system. And if you just take an arbitrary ket, one thing we know that we can write this as C plus 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 C minus minus. So let's just rotate it by 2 pi. So a rotation by 2 pi is just one full rotation, and naively we would expect our system to rotate to its initial state. If you look at the expectation values, well, if you remember the form of the expectation values, they just would rotate with cosine theta, sine theta, and a rotation by 2 pi would actually just leave the expectation value of vectors invariant. So the expectation value of Sx will not change under a rotation by 2 pi. But the problem is when you look at what happens to the kets, you see this ket, after a rotation by 2 pi, we can write it as cosine pi times 1 minus I 2 over h bar is z sine of pi acting on alpha. Well, sine of pi is 0, cosine of pi is minus 1. So after a rotation, the rotated ket, if we rotate by 2 pi, is minus the initial ket. So at least for spin 1/2 systems, our state ket does not go back to the initial state. It acquires a minus sign. Well, since there is just a minus sign difference, the expectation values do not change, because in the expectation values we have the bra and the ket of the same state, both of which acquire a minus sign, and hence the expectation value does not change. But the ket itself changes. Yeah, okay, let me write it a bit more explicitly. 2 pi over 2. You see here we have rotation is theta over 2. In fact, that 2 is the reason why we get this minus sign in our ket. It's a property of spin 1/2 systems. Well, also for spin 3/2, spin 5/2, we will always get this minus sign. Now, the question is then, okay, there is this minus sign. Is it measurable? Can we measure that minus sign? Or, well, in the expectation values, we cannot measure this minus sign because basically expectation values do not change under 2 pi rotation. But what we can actually measure is this 2 over there, which is closely related with that minus sign. So how does these states rotate? Do they rotate by an angle theta or by an angle theta over 2? Now let's look at an example. Well, the example we will be considering is basically neutrons in a magnetic field. Well, we had already studied this problem. We had looked at electrons in a magnetic field. And we had seen that the spin of an electron in a magnetic field basically just keeps rotating. Now we can look at the same problem from a different perspective. Well, if you have any system in a magnetic field, its interaction with the magnetic field will be given by minus mu dot B. Now we can just assume that B is uniform and it's in the z direction. And the magnetic moment of the neutron, it will be proportional to its spin with a proportionality constant given by, let's say, Gn h bar over 2 m neutron times c. And for the neutron, Gn turns out to be something like minus 1.929, something around that number. Okay, the neutron is a neutral object, but nevertheless we know that it's made up of charged quarks. So although it doesn't have a total charge, it still has a magnetic dipole moment due to its spin. So you can, if you want to think of it classically, okay, there are these charges, but the charges are rotating in the neutron, creating a non-zero total magnetic dipole moment. So we know the Hamiltonian. Sz times p. Let me just write this as minus omega Sz.
Magnetization.
Mu(n) is the magnetic dipole moment.
H.
Which H? This is the Hamiltonian. So it has a Hamiltonian. Well, let me check the numbers. Okay, there's no H bar. Okay, there's an E, G, and E, B over M and C. Okay, so this is our Hamiltonian. So the neutron starts from a state alpha. Let's say at t equal to 0. So what is the state at some later time t? So what's the cat at a later time t?
To the power of minus
ht. This is equal to exponential of minus I over h bar minus omega s set of t. Or exponential of I omega s over h bar t. Well, let's look at, for example, the expectation value of Sx at a time t. This is nothing but the expectation value of e to power minus I omega s over h bar t Sx e to power I omega s over h bar t. Of course, this is at t equal to 0. But you see, that operator is nothing but rotations around the z-axis. You see, if you look at how we define the rotations around the z, well, okay. The rotations around the z-axis is given by this expression over there. So this is nothing but rotation by an angle theta is equal to minus omega t. So this is why with time it precesses. Sx at 0 cosine of omega t plus Sy of 0 sine omega t. Now, okay, so how will this help to measure that 1/2 in the evolution of the state ket, this 1/2 factor over there? Now, let's imagine such a thing. Let's suppose we have a source of neutrons traveling, and then we split them. 1/2 goes in one region, the other half goes through some other path. Here we put a screen, and along one of the paths we have a magnetic field. So you see, normally, let's say this is x0, this is x final. X final, the amplitude that if it starts from x0 at the time t0, that it will reach x final at the time x final, we'll have two amplitudes. Let me give some this. This is A, this is B, path A and path B. There will be an amplitude for it to go through path A. Let me put B over there, although there's no magnetic field over there. Plus there will be another amplitude that it goes through B. Now this B will be the amplitude that it will go through path B multiplied by e to power I omega t over 2. Now omega is this rotation due to the magnetic field, and t is the time it spends in the region where there is a magnetic field. So basically, Ca of B is actually independent of the amplitude. So you see that the interference pattern on the screen, this is Ca, no magnetic field, plus Cb, no magnetic field, e to power I omega t over 2. You see the interference pattern depends on this magnetic field. And, well, you can just set up the size of your region, which has a magnetic field. You can choose the velocity of your neutrons, so you can fix t, for example. You can change your magnetic field. That would be easier to change, the magnitude of the magnetic field. So you can just see how the interference pattern changes as you change B. So if, for example, delta W, the change in delta W, T over 2 is equal to 2 pi, let's say, or delta W is equal to 4 pi over T. You see, you have, by devising your setup, you have fixed what T should be. If this is, well, let me write it in a different form. 2. Now, for this value of delta W, and remember delta W, you know everything in delta W. You know the magnetic type, gyromagnetic ratio of neutron, you know the electric charge, you know Mn, the mass of the neutron, you know C. You can change W by just changing the magnitude of the magnetic field, B. And as you change B, starting from 0, when W changes by 2 pi over T, or 4 pi over t, the interference pattern should go back to its initial shape. Because in that case, this delta omega t over 2 is just 2 pi, and e to the power 2 pi times I is just 1. So you start with 0b, you start turning it on, and you start increasing your magnitude, and you see when the interference pattern goes back to the initial pattern. And then you measure what the delta W should be. If that delta W is 4 pi over t, the first time that the interference pattern goes back to the initial pattern, then you know that there is this factor 2. If the interference pattern goes back to its initial value after 2 pi over t rather than 4 pi over t, then you know that there is no that factor 2. That factor 2 is absent. So without that factor 2, that is, if the state after a 2 pi rotation goes back to the initial state, then your interference pattern should basically go back to its initial value when you change your W from 0 to 2 pi over t. If there is that factor 2 and hence your ket acquires the minus sign after a rotation of 2 pi, then this delta W should be 4 pi over t, not 2 pi over t. And this experiment is basically done. In your book there is no, the experimental values are not here, but basically this is the idea of the experiment. Now of course this doesn't measure directly the minus sign, but it measures this factor 2. And that factor 2 is the reason why we don't get the initial state after a rotation by 2 pi. Well, here the rotation is, we are not really rotating the system, just considering a rotation, but it's the magnetic field that basically rotates my system. Because the effect of the magnetic field in this system is exactly the effect of a rotation around the z-axis, around the magnetic field. Any questions?
Hocam magnetic field'de yani biz orada bir faz farkı yaratıyoruz değil mi?
Yes.
Bu da soldaki interference'ı görürüz. Optik değil mi zaten?
Exactly. We started from the optical analogy, because there are certain things, certain observations we have that we thought were only a characteristic of light and not matter particles. But quantum mechanics told us that no, even for matter particles, they behave almost like light. They interfere. And if you change the phase, you change the phase difference, you change the interference pattern. And then this allows us to measure how the phase of states changes. Well, we cannot directly measure the phase, the overall phase, but we can measure phase differences. So this is basically what we are doing over here. We cannot measure how much phase a state acquires. This minus sign that we are looking for, if you just take your system and rotate your system as a whole, rotate everything in your system, it only gives you an overall minus sign which we cannot measure. So in this system, what we do is we just divide our system into two. One of them we rotate. Well, that rotation in this case is just like the time evolution is just like the rotation in this case. The spin is rotating around the magnetic field. So that magnetic field rotates my part of my system, but it doesn't rotate the other half. So basically, due to this rotation, there is a phase difference created. And that phase difference is creating the interference pattern. So using this setup, we can measure how much phase will be acquired due to the magnetic field. And then the easiest thing to measure would be, for example, okay, if you have a phase difference of 2 pi, nothing changes. That would be an easy measurement. So you just measure how much magnetic field you need to go back to the initial interference pattern. And it turns out that to be the necessary magnetic field, the necessary change in the magnetic field will create an angular frequency which is given by 4 pi over t, t being the time the system spends in the magnetic field. And if there is no if this factor of 2 were absent, it should have been just 2 pi over t. So that's why how we conclude that if you rotate your system by theta, your kets are not really rotating by theta, they are rotating by theta over 2. This 2 over here. Or this theta over 2 over here. This is valid for spin 1/2 systems. Since it is rotating by theta over 2, it is a rotation by 4 pi, which causes my system to go back to the initial state. A rotation by 2 pi turns out to be not enough. Other questions? Okay, so let's start with a different formalism. Whenever we are talking with spins, we usually don't talk about these operators most of the time. What we talk about is what's called the two-component formalism. You see, we have these two states. There is the plus state. Well, we just choose to denote it by this column matrix 1, 0, and the minus state, we choose to denote it by 0, 1. We are just writing matrices. And once we make this identification, these spin matrices, spin operators, turn out to be in their matrix form h bar over 2, just sigma. And these sigmas are what we call the Pauli matrices. Sigma 1 is 0, 1, 1, 0. Sigma 2 is 0 minus I, 0. Sigma 3 is 1 minus 1, 0, 0. Well, if you have any object alpha, we can write this as alpha plus, 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 alpha minus, minus. Well, if you want to show it in matrix form, this is plus alpha and the inner product of alpha state with plus. The plus ket, we show it by this column 1, 0. The minus ket, we show it by 0, 1. So any ket alpha, we can just show it by this column matrix. This object is what we call a spinner. It's not a vector. It's used to show the spin, so that's probably where the name comes from. This or is just from the vector. So it's not a vector, but it's still something used to show some kind of a direction. We can talk about the direction of the spin, so it's just given the name spinner. And this matrix, we can, quite often it will be shown by such a symbol instead of the cat. Now then, of course, we have the matrix elements. Of alpha and beta. Well, you can just write this as beta plus Si plus alpha, beta plus Si minus alpha, beta minus Si plus alpha, beta minus Si minus alpha. Well, you see, if you look at these first lines, it's in a sense nothing but plus it's like matrix multiplication. Well, Si in terms of its matrices, it's h power over 2 sigma I. We are multiplying it with the matrix alpha plus alpha minus, but that is nothing but matrix chi. Let me use this chi alpha to denote that it corresponds to the column matrix of the ket alpha. And we look at the plus component of this. You see, h power over 2 sigma I is a 2 by 2 matrix. Chi is a column matrix. So if you multiply a 2 by 2 matrix with a dimension 2 column matrix, you get a column matrix. So that expression in square brackets is a column matrix. And we are looking at one of the components. The plus component is the top component. How do I know that it is the plus component? Well, it's this one. I am summing over the components of the chi alpha. What remains is the component of the matrix sigma. And the other one, the other two lines are nothing but h power over 2 sigma I chi alpha, the minus component. Or this I can write as chi beta, the plus component, h power over 2 sigma I chi alpha. Well, the plus component is the first component, plus chi beta, minus component is the second component, h power over 2 sigma I chi alpha 2. But this is nothing but, well, I just multiply the first component of first column matrix with the first component of the second one, and the second components together. This is nothing but chi beta transpose. Well, let me put the complex conjugate also here. So this is dagger times h power over 2 sigma I chi alpha. So basically we have this, that the matrix element of Si between these two states is nothing but take the first one, the matrix corresponding to the first one, it's dagger h power over 2 sigma I, the second one. Now, sigmas have some interesting properties. We already know that Si, Sj, commutator is I h bar epsilon ij k sk. These are h bar over 2 sigma I, h bar over 2 sigma j. This is equal to I h bar epsilon ij k sigma k over 2 h bar. So these h bars on the left cancel the h bars on the right. One of the twos on the left cancel the 1 over 2 on the right. So we obtain sigma I, sigma j. Their commutator is twice I epsilon I j k sigma k. Now, if you look at their explicit expressions, so for example, let's see sigma 1, sigma 2. 0, 1, 1, 0, 0 minus I 0. This is I 0, 0 minus I. Well, sigma 2, sigma 1, this is nothing but sigma 1, sigma 2 dagger. This is nothing but minus I 0, 0 minus I, or sigma 1, sigma 2. So if you just change their order, they change sign. Sigma 1, sigma 2 is minus sigma 2, sigma 1. Or sigma 1, sigma 2 plus sigma 2, sigma 1, this is equal to 0. Or their anti-commutator, in fact, you can just show that whatever sigma i's are, sigma I, sigma j, is always equal to 0 if I is different than j. If you just take two sigma matrices, if you change their order, they change sign. You can talk about their squares. If you take sigma 1 squared, 0, 1, 1, 2, this is equal times 0, 1, 1, 2. This is 1, 0, 0, 1, which is nothing but the identity matrix. Well, in fact, you can just do it for the other ones. Sigma 2 squared is 1. Sigma 3 squared is 1. So if you go back to this anti-commutator, we know that if I and j, they are different, this is 0. Well, if I and j, they are the same, both are the square of sigma matrices, so both are the identity matrix, so it's just 2. So this is equal to 2 if I and j are the same, twice the identity matrix, and they are 0 otherwise. So these are the properties of the sigma matrices, the Pauli matrices. Now, we can use these two properties, well, sorry, here I have a 2, to drive certain relations about sigma matrices. For example, let's look at sigma matrix, and let's multiply it with an ordinary vector, and take another sigma matrix, multiply it with another vector. And let's calculate this matrix product. This is equal to sigma I, AI, sigma j, bj, which is sigma I, sigma j, AI, bj, which I can also write as 1 over 2 sigma I, sigma j plus sigma j, sigma I plus 1 over 2 sigma I, sigma j minus sigma j, sigma I. Times AI, bj. Well, in that parentheses, the second terms, they cancel. One comes with a plus, the other one comes with a minus sign. The first terms, they just add to give a coefficient 1, which is nothing but my previous line. So I just didn't do anything. In the previous line, I just divided into two parts. And then in each part, in one of them, I added the reverse product. In the second one, I just subtracted. Now, the reason is I already know what these combinations are. So this combination is twice Kronecker delta ij. And this combination over here is twice I epsilon ij k sigma k. So this is equal to Kronecker delta ij plus I epsilon ij k sigma k ai bj, which is a dot b plus I sigma dot a cross b. So we have such an identity. Well, let's see, where can we use this? You see, we already know how, at least if we have a particle that doesn't have a spin, we know how it interacts with an electromagnetic field. You just replace the momentum with P minus Q over Ca. And you determine how the charged particle interacts with a magnetic field. What about the spin? How does the spin interact with the magnetic field? Does it interact with the magnetic field? Well, experimentally, we know that it interacts with the magnetic field. Here, we had already used that fact in this derivation, that if an object has a spin, it has a magnetic dipole moment, which interacts with the magnetic field. Let's derive it. How do we get that? Well, let's start with the Hamiltonian. Let's assume we have a free Hamiltonian. You see, we had already discussed that we don't really know what the Hamiltonian is. So we are just making some guesses. There are certain criteria that we use that at least we should be able to somehow recover the classical equations of motion. That is one thing that's one of the criteria we use. It should respect the symmetries that we observe, like the rotational symmetry of the universe. So nothing changes on the rotation, the Hamiltonian should respect it. But besides these few criteria, we don't really know what there is not much criteria to impose on the Hamiltonian. I can write exactly the same Hamiltonian like this. Well, you see, in this expression at the top of the screen, just assume A and B are the momentum operators. If they are the momentum operators, then P cross P is just 0. Since P cross P is 0, I am left with the first one. So I just hope sigma dot P squared is nothing but P squared. Now I can use my prescription to add how the magnetic field, how my prescription to describe the interaction with the magnetic field. So this is for B is equal to 0. If this is the correct prescription, let's say, for if there is a magnetic field, my new Hamiltonian is sigma dot P minus Q over Ca squared over 2m, which is sigma dot P minus Q over C sigma dot A squared over 2m, which is equal to sigma dot P squared over 2m plus 1 over 2m minus Q over C sigma dot A squared plus minus Q over C sigma dot A sigma dot P plus sigma dot p sigma dot a. Times 1 over 2m. So my Hamiltonian for a spin 1/2 particle with a within a magnetic field is p squared over 2m plus 1 over 2m q over c squared a squared, because sigma dot a squared is just a squared, plus, well, here in the second expression we have to be a bit careful because this a and p, they do not commute. So that's the part we have to pay a bit attention to. So we end up, let's just write it in a slightly different form, 1 over 2m minus q over c, sigma I, sigma j, ai pj plus pj ai. Well, I had already calculated that sigma I, sigma j is nothing but Kronecker delta ij plus I epsilon ijk sigma k. Now the first term is nothing but just the ordinary, this term doesn't refer to spin, whether my particle has a spin or not. That is exactly the same Hamiltonian. Similarly, this term, well, it doesn't depend. It's like a potential. Again, it doesn't depend on the spin of my particle. I mean, if it even for a particle which doesn't have a spin, I would obtain that term. Similarly, this Kronecker delta ij term is the same whether my particle has a spin or not. The spin-dependent part is this one over here. So the spin-dependent part of my Hamiltonian is 1 over 2m minus q over c, I epsilon ijk, sigma k, ai pj plus pj ai. Now let me do a bit more. Okay, so let me look at one of these terms, ai pj. Well, this is equal to epsilon ijk ai pj minus aj pi. Do you follow this? Are you familiar with this property? Okay, let me derive it. That is equal to 1 over 2 epsilon ijk ai pj plus 1 over 2 epsilon j I k aj pi. I just wrote that term as 1 over 2 that term plus 1 over 2 exactly the same term. But in the second one, you see I and j, they are just dummy indices. I'm summing over them. I can just change their name. Instead of I call it j. Instead of j, I call it I. But now this epsilon jik is nothing but minus epsilon ijk. It is antisymmetric under the exchange of any two indices. So I end up having 1 over 2 epsilon ijk ai pj minus aj pi. Now I have epsilon ijk AI pj plus pj AI, which is nothing but 1 over 2 epsilon ijk AI pj minus aj pi. This is the first term. While the second term is pj AI minus pi aj. Now I have this AI pj plus pj AI. This is equal to AI pj plus AI pj minus or plus pj AI. Now, pj_ai, we had already seen before that is nothing but h bar over I, derivative of ai with respect to xj. That's basically the term I would be interested in. So if we go back, this is equal to 1 over 2 epsilon ijk. Well, AI pj plus pj ai is this sum. This is AI pj twice plus h bar over I del over del xj ai minus, for the other term I can also write twice aj pi minus h bar over 2 xi aj. Well, you see that derivative just gives me the curl of A, but the curl of A is nothing but my magnetic field. That term will give me the interaction with the magnetic field. And if you look at the interaction with the magnetic field, that is the term I am interested in. Well, there are these terms. One over, let me just copy this one. H spin is equal to 1 over 2m minus q over c I epsilon I j k sigma k times 1 over 2 epsilon I j k h bar over I del over del xj ai plus I have other terms 1 over 2m minus q over c I epsilon I j k sigma k. Well, these i's, they will cancel. 1 over, okay, this 1 over 2 will also cancel. That will, well, I have this term and this term, I can just add up to cancel that 1 over 2. There is no epsilon ijk, there is just single one. Times h bar del over del xj ai, and that derivative, now this I is cancelled, 1 over 2m minus q over c h bar sigma k, that is a curl of A minus the curl of A, the K component. And finally, we have 1 over MC minus Q over MC H bar over 2 sigma K times BK Q over MC S dot B. Well, Q over MC was nothing but the magnetic dipole moment. If you go back to our initial expression that we used for the spin magnetic field interaction, we have a Q over MC times SZ. Well, there is this Gn over 2. Well, usually this is written as G, which is called the gyromagnetic ratio, Q over 2 MC S dot B. And it depends on the internal structure of the particle mainly. And in this case, it turns out to be for fermions, it is 2 in this approximation, let's say. And for electrons, for protons, etc., it turns out to be very close to a factor of 2. Now, any questions up to here? Let's give a break, and then we can continue.